Okay, now that we've got these shortcuts that we were working with, I want to go back and kind of redo a little bit about this idea of determining when a function is differentiable. And so, because you're going to see these problems, but now that we have the shortcuts, we want to make sure that we really understand kind of this process, and we'll use the shortcuts to our advantage. Now, if you'll recall, okay, so this is from the last chapter, that a function f of x is differentiable if two things occur. If f of x is continuous, that's number one, and two, you want to make sure that it is also smooth, that it has no cusp and no vertical tangents. And this was the first part is pretty straightforward. We did several of those. But the second part was a little bit difficult because when we were doing this in chapter 2, we were using the limit definition in order to find it. So now this is going to become a little bit easier problem because in order for me to do this, I basically just need to use the shortcut rules. So let's kind of recap what we would do. Let's talk about part 1. Let's talk about continuity. Alright, so first thing is your two pieces, since we have piecewise, both pieces are continuous, and that's we love the nice easy one because they're both polynomials. 3 minus x and ax squared plus bx are polynomials. So the only place where we have some concern is at the boundary curve. So we need to check continuity at x equal to 1, where it switches from one piece to the other. That's the only place where we might have some type of a jump discontinuity if they don't happen to meet. So remember the three parts of the definition of continuity. The first part is f of 1 had to exist. We have an equals right here, so if I plug 1 into that piece, I would get a plus b, so it exists. So we're good with that. Our second part is we need to check the limits, the left and the right. So I'm going to check the limit as x approaches 1 from the left of f of x. We show that we know that on the left side, we're going to be using the piece. Here's x less than 1, so the left piece would be 3 minus x, which would be 3 minus 1, or 2. The limit as x approaches 1 from the right on this function, you would use the right piece, ax squared plus bx, which since it's polynomial, we can just direct substitute a plus b. Okay? And what we're basically doing the left and the right limit for is because we needed to have the limit as x approaches 1 of f of x has to exist, and it exists when a plus b equals 2, when the left and the right limit are the same. And we know that it is continuous at x equal to 1 when a plus b equals 2, because that would make f of 1 equal to the limit as x approaches 1 of f of x. Okay? So as long as this fact is true, okay, we haven't found a and b yet, but as long as this fact is true, the function is continuous. So now we come down here to differentiability. Okay. Which is really what we're checking. Now that we know that we are continuous, we want to check and see whether or not we have a smooth, no cusp function with no vertical tangents. We already don't have to worry about your discontinuities because I just proved that it was continuous everywhere. So now, well, everywhere provided that a plus b equals 2. So I want to make sure that I'm smooth, have no cusp, and I have no vertical tangents, which means I basically just want to make sure that the derivative exists. Okay, so basically what we want to do is to see that it's smooth and we have no vertical tangents is we want to make sure that the left and the right slopes merge smoothly, okay? So left and right slopes, aka derivative, merges smoothly, and we want to make sure that they're not vertical. That's the other thing. They're not infinity or negative infinity. Now, when we had done this in the past, okay, kind of as a review, we would do the limit as x approaches 1 from the left of the derivative function. And we would have done the, because we're doing the derivative, we would have done f of x using the alternate form minus f of 1 over x minus 1. Okay? We could have also done, and then we would also then, of course, do the right, the limit as x approaches 1 from the right of f of x minus f of 1 all over x minus 1. And we would have made sure that they were the same. That's the whole smooth part of it, that we wanted to make sure that those two are equal to each other. We could have used, instead of the alternate form, done a limit as h approaches 0 of f of 1 plus h minus f of 1 all over h. Use that definition. Gone to the left and then gone from the right as h approaches 0 from the right of f of 1 plus h minus f of 1 all over h. So we could have done that as well. And those were kind of a long process. But basically what you're trying to do is you're really just trying to figure out if the derivative is smooth at that point. Is the derivative continuous at x equal to 1? So what you're basically going to do is now, we have all the shortcut rules, and that's basically what we're doing, is we're calculating the left derivative and we're calculating the right derivative. Well, we can do the left and the right derivative in about 2 seconds using our shortcut rules. So what we're going to do instead of this, okay, so now here's our shortcut to what we had done before. We're going to calculate the left and the right piece. The left piece derivative would be negative 1 if x is less than 1. Your right piece derivative would be 2ax plus b, 2ax plus b, if x is greater than 1. Now notice at this point I'm not commenting about 1 yet, because I'm not going to put in equals because I don't really know whether or not it exists. And what I want to make sure here, I'm not going to plug 1 in and plug 1 in here. What I want to make sure is that I need the left and the right piece of the derivative to merge smoothly. So left and right derivatives must merge smoothly, and they must exist, and exist, which basically means the limit as x approaches 1 from the left of this derivative function has to be the same as the limit as x approaches 1 from the right of this derivative. Okay? So that's the merge smoothly part. I don't have to worry about the pieces themselves because in differentiability, both the left and the right piece were polynomials. So since 3 minus x and ax squared plus bx are polynomial, they are differentiable. So we're only concerned that we have, just like the concern that we have up here, we need to check differentiability at x equal to 1. So we only need to check and make sure that they merge smoothly together. So I'm now going to look at this is what we need to happen, the limit on the left equal to the limit on the right. So the limit on the left the limit as x approaches 1 from the left on the derivative would be the limit as x approaches 1 on the left of the left piece, which is a constant, so I get negative 1. The limit on the right of the derivative would be the right piece of the derivative, which is 2ax plus b, which is polynomial, so I can direct substitute, and I end up with 2a plus b. And so it would only be differentiable at x equal to 1 when 2a plus b equals negative 1. So notice at this point I still haven't found a and b. I have just found two conditions that must be true. Okay? My two conditions, so now we're actually going to do some work and find a and b. My two conditions are that a plus b equals 2. That's what gave me continuity. But remember, being continuous is not enough to be differentiable. To be differentiable, I also need 2a plus b to equal negative 1. So I basically have a system. So the idea here is this part was much shorter because all I really have to do is find the derivative of each piece and make sure they merge smoothly, which is look at the left and the right limit of the derivative. That's the shortcut. I don't have to do these limits doing it the long way to calculate the derivatives. All I have to do is look at the derivative itself, left and right piece, and make sure that the limit is the same. So now that I have my system, then I'm just going to do a quick system solve. Let's go ahead and just multiply this by negative 1 and add it to that one. So we have a minus 2a, b minus b, and then 2 plus 1, which is 3. So a would be negative 3, and when a is negative 3, b would have to be 5. So when a equals negative 3 and b equals 5, f of x is differentiable everywhere. All right, so that's just another example coming back to our how do we basically do a free response problem where we have to show that a function is differentiable. We still have two parts. We have to show that it is continuous because continuous is a requirement for differentiability. And then you also have to show that it merges smoothly together in a way that we don't have vertical tangents or cusps. And so the idea is we get a shortcut, and our shortcut is we can find the derivative of the left and right pieces and simply make sure their limits on the left and the right are the same. Okay? And so that will wrap up our section here in section 3.2, and we're ready to practice some problems on this.